On to the next part, and we're going to apply whatever we've learned up to now to solve maximum and minimum problems. So we're going to get questions like this, where the surface area of a solid cuboid is 100 centimeters square, and the volume is v centimeter cube. First, we're just told to express h in terms of x. So remember, the surface area is just the area of each surface on the cuboid. So for the upper surface and the lower surface, we're going to have x times x. So we're going to have 2 times that to get the area of both these surfaces, the up one and the bottom one. Then for all the ones in the side, we have h times x. So we're going to have 4 times h times x to get the surface area of all the 4 side surfaces. And if you add them together, you're going to get the surface area of that entire cuboid, and that's going to equal to 100 centimeters square. Therefore, 2x squared plus 4hx is equal to 100. We need to make h the subject. So we can subtract 2x squared on both sides. We get 4hx equals 100 minus 2x squared. Then we can divide by 4x on both sides, and we get that h is equal to 100 minus 2x squared over 4x. Or we can even do it separately, where we get 25 over x minus a half x, and that's going to equal to h. Now on to b, we're told to show that the volume v is equal to 25 times x minus a half times x cubed. So here the volume is just going to be x times h, right? So x square h is equal to v, but we know that h is this thing right here in terms of x. So we can just have x squared times 25 over x minus a half x, which is going to give us 25x minus a half x cubed, and that is going to be our volume v. So that's part B done. Then in part C, given that x can vary, find the stationary value of v and determine whether the stationary value is a maximum or a minimum. So to find the stationary value, remember, we take the derivative of that thing that we want to find the stationary value of. So in this case, it's v with respect to x. So we basically want to find dv over dx, the derivative of v with respect to x. And that is going to be 25 minus 3 over 2x squared. And you want to find the stationary value. That means when dv over dx is equal to 0, that means 25 is equal to 3 over 2x squared. Therefore 50 equals to 3x squared. And so 50 over 3 equals x squared. So the square root of that thing right there, which is going to give us x equals to positive root 50 over 3 and x equals to negative root 50 over 3. Now obviously we know that the value of x cannot be negative. Therefore the only one we're going to deal with is the positive value. And now we need to find whether that stationary value is a maximum or a minimum. For that we need to find the second derivative. Therefore of this right here, we find the second derivative, which is going to be negative 3x. After taking negative 3 over 2 times 2 times x power 2 minus 1, which is just 1. So negative 3x. And that is our d2v over dx squared. Then we can put in our value of x, which is root 50 over 3. So negative 3 times root 50 over 3. And that is going to be negative root 50, which is a negative value. That means that stationary value will be a maximum. What this tells us is when you have a surface area of 100 centimeters square, the maximum volume you can have for this cuboid right here is going to be when your x value is root 50 over 3. Next, the diagram shows a solid cylinder of radius r and height 2h cut from a solid sphere of radius 5. The volume of the cylinder is c centimeter cube. Express r in terms of h first. So if you can just zoom into this thing right here, we have something like this. We have the center of the sphere, which is also the center of the cylinder. Then it goes to one of the edge of the sphere and the edge of the cylinder, and that is 5 centimeters. Then from that center to the edge of the cylinder, that's going to be r. And you basically want this distance times 2. right? So halfway, this is just going to be h. Therefore, this right here is h. So we have a right angle triangle where the hypotenuse is 5 centimeters and the two sides are r and h. Therefore, what we have is r squared plus h squared equals to 5 squared according to the Pythagoras theorem. Therefore, r squared plus h squared equals to 25. Subtracting h squared on both sides, we get that r squared is equals to 25 minus h squared. Then to get r, you just square root both sides. So r equals to the square root of 25 minus h squared. Obviously, we're only going to deal with the positive value because r cannot really be negative. Then we want to show that the volume C, in this case, not V, is equal to 50 pi h minus 2 pi h cubed. That's the volume of the cylinder. The volume of the cylinder is given by pi r squared times h. So we have found the value of r. We can put that into the formula of the volume. Therefore, C equals to pi root of 25 minus h squared square times h. This gives us C equals to pi times 25 minus h squared times h, which ends up giving us 25 pi h minus pi h cubed. Remember, this is just for half the cylinder because we used the height as h, while the height of the entire cylinder is 2h. Therefore, we just take this volume right here and multiply by 2 to get the entire cylinder because we just found half of that cylinder. Therefore, we're going to get 50 pi h minus 2 pi h cubed, which is what we wanted. Then we are told to find the value for h for which there is a stationary value of v. Stationary value of v meaning find the value for h for which there is a stationary value of c. That means our dc over dh is equal to 0. And our dc over dh is just the derivative of this equation right here with respect to h, what the independent variable is. Therefore, we're going to find the differentiation of this equation, and we are going to get 50 pi minus 6 pi h squared. Remember, pi is a constant, so you just treat it like the number before. And you want that to equal 0. Therefore, 6 pi h squared is equal to 50 pi. Divide by 6 pi on both sides. We get that h squared is equal to 25 over 3. Taking the square root on both sides, we get that h is equal to 5 over root 3. Rationalizing this will give us 5 root 3 over 3. That's going to be our value of h for when there is a stationary value of c. Then to determine the nature of the stationary value, we have to find the second derivative. So d2c over dh squared. That's going to be taking the derivative of this thing right here. This is just a constant. There is no h value, so this becomes 0. This one right here, there is an h value, so you derive this as normal. So negative 12 pi h, that's going to be our second derivative. Then we can put in this value of h. We're going to get negative 12 pi times 5 root 3 over 3, which will give us negative 20 pi root 3. This is going to be a negative value. That means that stationary value will be a maximum stationary value. That means for the information that we've been given, for a sphere of radius 5 and the cylinder being inside that sphere, the highest volume that we can get for that sphere will happen when our value for your height is 5 root 3 over 3. One final example, the diagram shows a hollow cone with base radius 12 centimeters and height of 24 centimeters. A solid cylinder stands on the base of the cone and the upper edge touches the inside of the cone. The cylinder has base radius r, height h, and volume of v. So remember, this cylinder can have different heights and different radiuses. That it can also be a taller cylinder. Okay? That's what the problem is saying. So when can we get either a maximum or a minimum volume for that cylinder right there while being bounded by that cone? So first we need to express h in terms of r. Then what we know from this is that this triangle right here is similar. For those of you who have done similarity and congruence in IGCSE, this triangle is similar to the bigger triangle that we have. And the way we know that is because it shares an edge with it. So for this smaller triangle, the values here are 24 minus h, and here the values are. Then for the bigger triangle of the cone, the height is 24 and the base is 12. And when we have similarity, the ratios are shared. Therefore, r over 12, this divided by this, so the similar side values is going to be the same as the ratio of the other similar side. So 24 minus h over 24. From that, we want to express h in terms of r, so make h the subject. We can multiply 24 on both sides. And this will give us 2r equals 24 minus h. Then rewriting this will give us that h equals to 24 minus 2r. That's going to give us a value of h in terms of r. Then to show the volume of that cylinder, remember it's going to be pi r squared h. But our h is 24 minus 2r. So we're going to have that pi r squared times 24 minus 2r, which is going to give us 24 pi r squared minus 2 pi r cubed, which is what we wanted to show was v. Then we are told to find the volume of the largest cylinder that can stand inside the cone. So for that, we want to find the value of r such that we're going to have a maximum. And the way you find maximums for equations like this is by finding stationary points. Therefore, the first thing we'll do is find the derivative of this, which is the derivative of v with respect to r. And that is going to equal to 48 pi r minus 6 pi r squared. And you want the stationary value, so you want this to equate to 0. What we can do here is just factorize it further. We will get 6 pi r on the outside, then 8 minus r equals 0. Therefore, either 6 pi r equals 0, which gives us our r value of 0, or 8 minus r equals 0, which gives us our r value of 8. When r is 0, the volume is just going to be 0. So that's not the largest cylinder that can stand inside the cone. When r equals to 8, and we can confirm this by finding the second derivative, but I won't because it's just redundant. We already know that this is going to give us our maximum. We can then find the volume of that cylinder when r equals to 8. So 24 pi 8 squared minus 2 pi 8 cubed, and that is going to give us our volume. This right here is going to be 512 pi. So that's going to be the volume of the largest cylinder that can stand inside this cone right here with these heights and base.